So what I'm going to talk about is a little bit different from previous talks. And here I'm going to talk about more about the grounding between conversation participants. So we know common ground establishing common ground is important for smooth communication. So common ground can be defined as a collection of mutually agreed beliefs or knowledge. So for example, in situated communication where participants are co-present in a physical environment, we share a joint perceptual basis. So what that means is, can you hear me in the back? Up or down? You want me to do this? Oh, okay. Thanks. Okay, so this is better. Thank you. So being physically co-present, we have the perceptual access to the same part of the physical world. So for example, we're all here, and I'm talking about this projector, and I believe you all see this projector as I do. And if there's a loud noise happening in the hallway, and I believe you're going to hear that loud noise as I do. So because of that, because of this joint perceptual basis, I could use referring expressions like this projector, that noise. Okay, so I expect you have no problem of understanding me. So this joint perceptual basis enable language understanding and referential grounding. So let's take a look what happens in the human-robot dialogue. Suppose the humans and the robots are co-present in this shared physical world. Okay, suppose in front of this table with many objects. And a human has a perfect perception, so the human's representation of this world is enriched. And a robot may only be able to recognize a few of these objects, so the robot's representation is impoverished. So although they're co-present in this physical world, they have mismatched the representation of the shared environment. So what's no longer held is the joint perceptual basis. So this will make communication between them extremely challenging. So one fundamental question is how to mediate perceptual differences for effective referential communication. So I have to pause a little bit here to say that this is a vision community. In the last decade, certainly a lot of progress has been happening in computer vision. So for these bunch of objects, there's no problem for a vision system to recognize them now. But what I'm more interested in is when the vision system fails, okay? When the vision system cannot perceive the environment as well as human do, what can human and a robot do to collaboratively to strive to maintain this common ground? So throughout this talk, in fact, what you're going to see is a pretty simple setup of the visual scenes, because this will allow us to easily manipulate the environment, allow us to really study the language behavior. So I'd just like to mention a few words of that. So I'm interested in when the vision fails. Okay. So before we answer this question, one fundamental question is, how do partners with mismatched perceptual capabilities strive to collaborate and reach common ground? So how do we answer this question? It is very hard to invite human subjects with measurable perceptual differences come to the lab to do the study. So instead, we developed a system to simulate mismatched perceptual capabilities. So what you can see here is this two computers connected through the network. At the one end is the director, and director is assumed to have the higher level of visual capability, and then at the other end is the matcher, who is assumed to have the lower perception capability. And so the director can see this original image with several objects, and some objects have certain names. And then the matcher will only see an impoverished view of the original image. So we'll just apply very simple computer vision algorithms to create this impoverished view. So we ask these director and the matcher to play a set of naming games. So director goal is to convey these names to the matcher, so the matcher knows which object has which name. So we'd like to study how humans, okay, when they have these mismatched perceptual capabilities, how they engage this drive to maintain the common ground. And next, I'm going to just show you a quick clip from the studies, the data we collected from the studies.
Very right, the rightmost of object is named Alexis.
You hear it?
ALEXIS.
Wait, so you said...
The big scissor.
Big scissor is Alexis, okay.
Yep.
Okay, this is Alexis.
Yep. The coffee cup is Brian.
Alright, I don't have a coffee cup. Where is it?
Alright, the coffee cup is to the right of the blue car.
And I don't have a blue car.
The blue car is right below Alexis.
The blue car is right below Alexis, and then so the coffee cup is
to the right of it. Yep.
Okay, so... And what's the blue car's name?
Austin.
Wait, Austin, what's the cup's name?
Brian.
This is Brian.
Yep.
Okay.
That's Brian.
Okay. And Austin is the blue car.
Yep, Austin's blue car.
This is Austin.
Now do you see a clip below Austin?
No, there's just something. Okay, that's...
So you get the idea. I'm not going to show the whole video. And so from these studies, we actually see that in terms of language-based communication, the object-based properties, spatial names, and the group-based spatial relations are commonly used in this referential communication. And we see the extra effort from the human player, the director. Instead of directly talking about a target object, giving the name, the director actually goes through some easily identified objects and gradually go to the target object. And we also see the extra effort from the robot player. So instead of saying that I don't see something, the robot player actually proactively describes what he sees from the shared environment. So we like to collect this kind of data, and then so we can build computational models to enable collaborative human-robot referential communication. That's the purpose. So given this data, we have studied different problems. So the first problem is the referential grounding, which essentially is the robot needs to understand in its representation which object in this representation referred to by the human linguistic expressions. So this reference resolution has been studied widely in language and the dialogue community, but here the difference is these expressions are created based on the human's rich representation, and now the robot will have to map this to his own representation. So because of this mismatch in the representation, this referential grounding can be challenging. It is not likely to resolve it in one shot. Usually it involves a collaborative dialogue discourse, as we see in the human-human study. So based on this, we developed a graph-based approach. So essentially, we use the dialogue graph to capture this linguistic discourse. So here, each entity represents a linguistic expression, and the edge represents the semantic relations between these linguistic expressions. And we can use a vision graph to capture the perceived shared environment. So here, each node captures the perceived object as well as lower-level numerical features. And given this representation, then the referential grounding can be formulated as a graph matching problem. Essentially, is to match the dialogue graph to the vision graph that maximizes the over-OR compatibilities between these two graphs. And then this over-OR compatibility actually can be defined by the mapping between the nodes and mapping between the edges, which are further measured by the what we call the word grounding models. So basically, what does the red mean? Okay, what does the red correspond to the lower level visual features? So to solve this optimization problem, there could be different algorithms. Just by applying a simple state-based search algorithm, we find that this graph-based approach can ground human utterances to misrecognize the objects with about 66% of accuracy. And if you remember from the human-human communication, when the robot doesn't understand something, for example, robot doesn't see an apple, the robot player often proactively provides what he sees in the environment. He says, I see an orange. And then the human could accept this presentation and expand further, okay, from this expression. So which means that in this collaborative discourse, agent also proactively create the linguistic entities in this dialogue graph. But what's nice about it here is that when agent introduce these entities into the dialog graph, it actually precisely know which object in its own representation this linguistic expression is mapped to. So this way, in fact, by incorporating what we call this is the agent present human accept strategy, which has actually happened quite frequently in the human dialogue data. If we incorporate these kind of a behavior into the graph matching, in fact, it will reduce the search space to find the matching hypothesis. So just by simply incorporating these collaborative pattern, we can improve the referential grounding with about 18% of absolute gains. And another thing to look at is throughout these discourse, there are a lot of expressions they tend to co-refer with each other. And instead of just make a commitment about those co-referring relations and make these dialogue graph, we can maintain all the hypotheses about these co-reference relations and then do it jointly. So if we do a joint co-reference resolution and referential grounding, it can further improve the performance, both the accuracy and efficiency. So we're not going into details about these algorithms. But we did incorporate these referential grounding algorithm into a NAO robot. So next I'm going to show you a demo of this robot actually working with the human the human teaches robot about different names of these objects. And what you can see here, this is what human sees, and this is what the robot sees in the environment. And we use the moped computer vision algorithm here. And here's the semantic processing. And these are the graphs, okay, the dialogue graph and vision graph. And I just want you, to bring your attention when you see in the demo, you're going to see some of the green labeled nodes. Those are the new knowledge automatically acquired through dialogue. Okay, so the robot used the knowledge acquired through dialogue to enrich its own representation during the interaction.
Hello, Darwin.
Hello.
Let's play a game.
All right.
The green cup is called Bill.
Understood. The green cup is Bill.
Do you see a car?
Yes, I see a car.
Do you see a blue can behind that?
I don't see a blue can. I see a blue unknown object there. Is that the can you are talking about?
Yes, it's Mary.
Understood. The blue can is Mary.
The red box is called Richard.
I don't see a red box. I see a white box there. Is that Richard?
No, it's to the right of the car.
I see a red cup there. Is that Richard?
Yes, it is not a cup, it's a box.
Sure. The red box.
The orange bottle on the left is called Katie.
Okay. The orange bottle is Amy.
Okay, so you got the idea that the robot and the human can carry conversation and can enrich its own representation, internal representation about the kind of objects seen in the scene and what's their name, so on, and the properties. Okay, so this is a just demo. We're interested in if we have a real human subjects come to our lab. Okay, what would be the the results? And oops.
No, it's...
Something's okay. All right. So, so we conduct empirical studies, and the objective of the study is to really study this collaborative effort in mediating perceptual differences. We're particularly interested in two dimensions of information. For example, the collaborative effort was specifically manipulated into two levels. Low level, basically, the robot just simply accept or reject a presentation from human. And high effort means the robot, instead of, in addition to reject and accept, the robot will proactively provide information about its own internal representation of the environment. And as we're interested in the mismatched perception, we also manipulated 2 levels of a perceptual basis. One is the low mismatch, means that the most of the objects can be recognized by the robot. So there is a low mismatch between the human and the robot. And a high mismatch means that the majority of objects, in fact, cannot be correctly recognized by the human, by the robot. So there is a high mismatch. So we have the subjects come in, and the setups like this, and perform. So this, okay, we have the it's a 2x2 factorial design. So resulting 4 conditions, each subject will perform 1 condition. And so in each task, there's 6 names, 6 objects to be named. And the task is considered complete if a subject believes he or she successfully communicated the names to the robot. So this is the belief, okay, subject's belief. And since we're working with the automated system, and often it can get into some kind of deadlock, and so we have these task abortion criteria. So if the robot fails to acquire any new knowledge within 3 minutes, so we abort the task, the robot would just simply say that, I'm tired, okay, let's take a break. So we have in the end, we have 96 dialogues under these automatically runs, and we only had 43 dialogues that led to perceived common ground. Basically, the human believes that they have successfully completed the job. And then the 53 actually led to the abortion. So for those aborted conditions, we ask these subjects come back after break, and we run those conditions again under the wizard systems. So wizard means that the wizard helps the system in terms of language processing, okay, provides the sort of close to ground truth performance to the language processing components. And so from the results, the first glance of this result seems to indicate that the low effort actually works better than the higher effort in terms of the perceived common ground. This is in perceived common ground, seems to work better, low effort. But actually, this is what this really means, that low effort can lead the subject to believe that a common ground is reached. But in fact, it is not. So this is even more detrimental, okay, than not even establishing this kind of making the people believe a common ground is reached. So what we really need to do is to measure the true common ground. In fact, we can do that. We can just look at the end of the dialogue, how many names are correctly acquired by the robot. So this is the true common ground. And the blue bars are the number of words, names correctly recognized by the robot at the automatic runs, and then the green is the wizard runs. And as we can see that, okay, these are the interaction plots between the perceptual differences and the effort. And as we can see that when the low mismatched perception, the effort doesn't make quite difference. But then where there is a high mismatch, the high effort makes a significant difference in terms of the grounding. And what also puzzled us is for those green bars, here the language performance actually close to Oracle, the ground truth, but then we still only get 4.5 out of 6 names correctly. So there are other challenges in terms of these grounding, even though language processing can be perfect. So as we can see that, because the grounding is really dependent on these compatibility between these 2 graphs, and the compatibility relies on the word grounding models, which can be affected by the changing environment, the lighting change, and the faulty sensors, and also individual differences. For example, people colorblind may use different words to refer to the color distribution. So the question is, can the robot assess the reliability of the word grounding during the communication and be able to automatically make adaptation? So we can formulate this. Essentially, the compatibility is just the weighted sum of these grounding models. And we can formulate this as an optimization problem and to learn those weights automatically during online interaction based on human feedback. So what we have found out, okay, if we use the same data to evaluate this approach, we can look at, okay, these are the different words, okay, there can be words talking about the object type, words describing color, describing location, describing different project relations like left, right, and near, close, proximity relations. As we can see that in the high mismatched condition, the object type word grounding has a big job, which means that this cannot provide reliable information to do the to do the referential grounding. And we can also see that in the high mismatched mismatched condition, only after 4 or 5 dialogues, the robot is able to learn that the weight for the object type should be dropped. Is not reliable. And we can also, the robot can immediately adapt that for the subsequent referential grounding. It can actually improve the performance. Okay, so next I'm just gonna switch gear talking about the other side of the coin of a similar problem. This is the language referring expression generation. So robot will also need to be able to describe its own representation so that human knows what the robot is talking about, right? So this referring expression generation is a subtopic in natural language processing, and mostly is about generating a single minimum descriptions that would allow the listener to identify the target information among a bunch of objects. And mostly this work is done using the artificially generated scenes or virtual environment. So there's a strong assumption that the agent has complete knowledge of the environment. But what happens in the human-robot dialogue is that, okay, so the robot here has impoverished representation. So for example, if the robot wants to talk about this object, okay, he would say a cup next to the phone, and the human would have no idea what the robot is talking about. In fact, we did this investigation. A leading approach can achieve over 85% accuracy under matched representation, but would only achieve 47% accuracy under mismatched perception. Okay, so this percentage performance drop really motivates a new method to do the referring expression generation. So in fact, as we already seen that referential communication is a collaborative process. So it's not just generating a single minimum description. So the previous work had also mentioned that the humans use different types of expressions, such as episodic. Here, the 2 or more easily distinguished episodes are generated towards the target object. And installment model, where is after each installment, solicit feedback from the listener before move on to the next. So this motivates us to develop a new model for collaborative generation model. So we apply the reinforced learning to learn a policy for generating these referring expressions. So we have the state representation, and we also model the actions to generate these referring expressions. And we use the function approximation to approximate these value function. Here, the goal is to learn these weights during the training associated with a bunch of features which capture the perception uncertainties, spatial relations, grouping relations, and so on. And our results have shown we use the crowdsourcing for both model training and evaluation, and the results have shown that the collaborative models significantly outperforms the non-collaborative models under the mismatched perceptual representation. Okay. And we also interested in, so these are just the web-based study, and we're interested in incorporate that into the real human-robot interaction. So we know the human and the robot both have bodies in the environment. They can also use nonverbal modalities such as gesture or eye gaze to make reference to the shared environment and provide immediate feedback. So we can just simply incorporate some gesture features, cause of a gesture, in the originally learned model, and we also keep track of the human gaze behavior during interaction. The interaction, so suppose the robot wants to talk about this this stapler, but it's actually represented as recognized as scissors. So then, so the robot will have a current state representation, will pick the action that maximizes value function. In this case, it was asked, do you see the scissors? And then the human would look at it and say no. And the feedback would change these, update the current state, find another action. Then the robot is going to ask, do you see the green object to your left? And then the human would, okay, so yes, and so on. So based on the feedback, the state will be updated, new action will be chosen until the human can successfully identify the target information. All right, so I'm not gonna talk about this. So we did also the studies with the real human subjects, and we intentionally make the vision performance with the high errors, okay, the not very high accuracy, because we're interested in these how to mediate this perception-based different representation. Okay, so here's what you see is the human wear this eye tracker. Okay, oh, I have to see.
Do you see Robot 3 in front of you?
Yes.
That group I was just talking about. Do you see an object on the right that is on the right within the group?
Yes.
Okay, so just now they're gonna show more. So this just show the interaction, how the feedback can be directly feeding the language generation models. Okay, so don't have to talk about. And so we can use the natural language to mediate the perception, and we can also use that to do the action learning, because during a human-robot joint task, it's not feasible to have large amount of data, and also it's not feasible to go through lengthy reinforcement learning. So what really is available to the robot is the human partner. So I have been working with the roboticist, Professor Ning Shi, to look into this using natural language dialogue to teach new actions. And here just show you a quick demo to see how that works.
Stack the green block on the left onto the green block on the right.
I cannot perform this task. Please give step-by-step instruction.
Move the green block on the left to the top of the green block on the right.
All right then.
Open gripper.
Okay.
Now you achieve the stack action.
Understood.
Sort the blocks by color.
What do you mean by this sort?
Put the red blocks in the brown box.
I cannot perform this sort. Please give step-by-step instruction.
Move the red block on the left to the brown box.
Sure.
Move the red block on the right to the brown box.
Understood.
So you got the idea, okay. So what I've talked about, share with you some of the problems we're looking at to mediate the perceptual differences to establish common ground between humans and robots. And the take-home message is that when we try to enable human-robot interaction, we really have to be aware of these perceptual differences, and the algorithm we developed will have to take into consideration of a collaboration and a social interaction. And so as you see, our settings are pretty simple, and you probably, I suppose you don't believe that I just truly care about the cup is Jane or Mary or John, right? So I'm really interested in is to integrate the language and the dialogue with computer vision on realistic scenes and the tasks. Like this morning, Song Chun has mentioned this communicative learning, that through natural language dialogue, knowledge can be conveyed to the system to have a better, to learn and to also have a better inference of the shared environment and the joint task. This is something that I will be interested in collaborating with Song Chun and Cai Ming and the UCL groups. Thank you.